In this video, we are continuing with our introduction to chirality, focusing on how to identify molecules that are chiral or achiral. So if we were to focus on a single molecule and we want to determine whether it can have stereoisomers, then we want to be able to distinguish chiral molecules from achiral molecules. So a chiral molecule cannot be superimposed on its mirror image. A chiral molecule cannot be superimposed on its mirror image. Achiral molecules can be superimposed. In other words, an achiral molecule and its mirror image is just the same thing. It's the same compound. So how do we identify a chiral versus an achiral molecule? One way is to use the mirror test. So if we have a molecule, we could build a model. We could build a model of the mirror image, and then we could move them around, try to line them up on top of each other, and determine whether they can be superimposed, which means that the original molecule is achiral, or if they cannot be superimposed, then it means that the original molecule is chiral. Okay, that works. That is very thorough. It's also very time consuming, and we might not always have a model kit with us. Another way to think about this is to look for a plane of symmetry. If there is a plane of symmetry present, then the molecule is achiral. Recall in the last video, we looked at some examples where if we had hydrogen, let's say some X and a Y. Keep in mind that these are really right in front of each other. We just write them offset to be able to actually see them. But what we have is a plane of symmetry that cuts right through this molecule here. So we could cut right through the X, right through the Y, through the C, and then the H is symmetric with the other H. So this is an achiral molecule because there is a plane of symmetry. This was one of the examples in an earlier slide that did not possess the property of handedness. A third way that we can try to identify chiral versus achiral molecules is to look for a chirality center. So a chirality center is where we have carbon connected to 4 different groups. So also on an earlier slide, we had an example where we had a hydrogen, and let's say we have an X and a Y and a Z. Here we have no plane of symmetry. If we were to cut through the Y, Z, and C, now we have H over here, but X over here. There is no plane of symmetry. If we did the mirror test, which we did on an earlier slide, we would see that this and its mirror image cannot be superimposed on each other. They are non-superimposable mirror image isomers. If we look at the carbon itself, so now just focusing on a chirality center, this carbon is a chirality center because it's connected to 4 different groups, a hydrogen, an X, Y, and Z. So connected to 4 different groups, that makes this a chirality center. A molecule that has one chirality center is a chiral molecule. If a molecule has more than one chirality center, we're going to talk about that later. We're going to see some examples where they are chiral and some examples where they are achiral. So let's look at a few examples and try to determine whether these molecules are chiral or achiral. And often the easiest way to do this is using method 3, looking for a chirality center. So this carbon is connected to 3 hydrogens, so 3 of the same thing. This is connected to 2 hydrogens, 2 of the same thing. This is connected to 3 hydrogens, 3 of the same thing. But this carbon is connected to a hydrogen, which is different from an OH, which is different from a methyl group, which is different from an ethyl group. So this carbon is connected to 4 different groups. So this is a chirality center. So we often label chirality centers with an asterisk. If we used method 2, we would look for a plane of symmetry. There is no plane of symmetry in this molecule, so it's chiral. If we used method 1, we would build a model, we would make a mirror image, try to line them up, and we would see that, nope, they do not line up on each other. So this molecule is chiral, and so it exists in 2 different forms. It could be like this, where we have our OH forward and our H back, or its mirror image would have the OH back and the H coming forward. So you would see that these are mirror images if you slid this one back behind this one. If we look at our second example, let's focus on this carbon, and it is connected to a hydrogen and an OH and a methyl, so those are 3 different groups, but it's connected to another methyl. Since it's connected to 2 methyl groups, then it's not connected to 4 different things. There is no chirality center, so this molecule is achiral. Another way we could think about this, if we draw it out in 3D, so thinking about the actual shape, we have, let's say we have our hydrogen coming forward, and then going back we have our OH. And let's imagine then that we have a plane of symmetry that cuts through here. So we could cut right through this hydrogen, carbon, right through this oxygen, hydrogen, and then that leaves the methyl group and the methyl group on either side of the plane of symmetry. So we have a plane of symmetry, or we don't have a chirality center, so this molecule is achiral. Looking at our third example, this one might be kind of obvious that we have a plane of symmetry that goes right through here. Alternatively, we could try to look for a chirality center. This is the only carbon that we might think about. It's connected to a hydrogen that's not shown, a methyl, that's 2 different groups, and then it's connected to this part, which is the same as this part, right? Because it's completely symmetric, and so it is not connected to 4 different groups. There are no chirality centers in this molecule, and there is a plane of symmetry, so we know that this molecule is achiral. If we built a model and built its mirror image, we would be able to superimpose them on top of each other because it's the same thing. And if we look at our fourth example, now if we focus on this carbon, so it's connected to a hydrogen and a methyl group, and it's connected to a CH2 and a CH2. But we don't stop there, because this CH2 is connected to another CH2, whereas this CH2 is connected to a carbonyl. So we go further than the first carbon. We can go to the second carbon, to the third carbon, to the 33rd carbon, until we find a point of difference. And so we do not have symmetry in this molecule. Instead, we have a chirality center at this carbon. And so with one chirality center, this molecule is chiral. So it exists as this, where we have our methyl group coming forward, or as this, where we have our methyl group going back. These molecules are not the same as each other. Let's imagine that we take this compound and we pick it up and flip it over like a pancake, so that we do this, giving us this group in front. Now, if we just slide this up here, we can see that they are mirror images of each other. But looking back at this orientation again, if we slid this ring on top of this ring, here our methyl group would be forward, here our methyl group would be back, so they do not superimpose on each other. So these are non-superimposable mirror image isomers. So we have a pair of enantiomers, or we can think of it this way as a pair of enantiomers. So this molecule is chiral. Here are a few naturally occurring molecules. Let's see if we can identify chirality centers. Looking at menthol, first of all, let's figure out which carbons we don't have to pay attention to. This carbon has two hydrogens that aren't drawn because it's connected to two hydrogens. They're the same thing, so obviously this carbon is not connected to four different groups, right? Same thing here and here. These methyl groups, the carbon's connected to three hydrogens, so they're obviously not chirality centers. But what about this carbon? So this carbon is connected to a methyl group and to a hydrogen that would be going back. And then this carbon is connected to a CH2 group and another CH2 group. But this CH2 is connected to a CO, whereas this CH2 is connected to another CH2. And so this group is not the same as this group, which means this carbon is connected to four different groups. So this is a chirality center. If we look at this carbon, it's connected to a hydrogen that's going back. It's connected to an OH. It's connected to this group, which is not the same as this group. So this one is also connected to four different groups. This is another chirality center. This carbon is connected to a hydrogen that's not drawn, that's coming forward. It's connected to this substituent. It's connected to this carbon and to this carbon. And so this group is not the same as this group and not the same as this group. And so we have another chirality center. So frequently, biomolecules have multiple chirality centers. Over here we have cholesterol, and if we look carefully, we will see that this is a chirality center because this carbon is connected to OH and H, and then this group is not the same as this group, so four different groups, chirality center. This is another chirality center. This group is different from this one, is different from this one, is different from this one. This is a chirality center. This is a chirality center. This is a chirality center. This one and this one. And I missed one. Oh, this one would also be a chirality center. So if we have a carbon that's connected to two of the same group, that is not going to be a chirality center. If we have a carbon that's double bonded to another carbon, to an oxygen, to anything, that means it's not connected to four different groups. So we can't have a chirality center at a double bond. But otherwise, if we have a carbon connected to four different groups, that is a chirality center. So trying to identify chirality centers is very useful because a molecule with one chirality center is chiral, and a molecule with more than one chirality center is usually chiral unless there is a plane of symmetry. So with these molecules, there's no plane of symmetry. We have multiple chirality centers. The overall molecule is chiral. Now, if we're trying to identify chiral molecules, sometimes we actually have to compare a pair of molecules. So let's say we're looking at a pair of molecules and we need to determine the relationship. We can see that this carbon is connected to four different groups. So this has a chirality center. This carbon is connected to four different groups, the same four different groups as the first molecule. So this is also a chirality center. So we know that this is a chiral molecule. We know that this is a chiral molecule. But the question is, are these enantiomers of each other, or are they just different representations of the same compound? Same thing down here. This is a chirality center because the carbon is connected to four different groups. This is a chirality center because the carbon is connected to four different groups. But is this the same as this, Or are these enantiomers of each other? One way that you could determine the relationship between them would be to build a model of this one, build a model of this one, and then compare your physical models. But if we don't have that available, we need to be able to manipulate the molecules on paper. So that means we have to imagine lifting them out of the paper, turning them, flipping them, rotating around bonds. And so getting practice doing this is going to be very, very important. Well, if we want to compare this molecule and this molecule, one way we can do this is to try to put these groups in the same orientation. So I'm going to leave this molecule alone, and I want to manipulate this molecule so that it's in the same orientation. So the first thing I want to do is pick up the entire molecule and flip it over horizontally so that we put the ethyl group in the same orientation as this ethyl group. So I'm picking up the molecule and I'm flipping it over so that we have, and I'm just going to call this ethyl. This is our OH. Because we flip the whole molecule over, now we have our methyl group in front, so Me for methyl, and our hydrogen is in back. Now we have our ethyl group in the same orientation as here. I want to put the methyl group in the same orientation. So how do I put the methyl group, which is currently here, I want it to be here. So now I need to rotate around this bond. So to do that, try to imagine that you are looking at these three groups as on a steering wheel, and we want to get the methyl group where the OH is. So imagine turning the steering wheel clockwise. So our methyl group moves up and then into the plane. So that puts, we have our ethyl group here, here's our carbon. I want to rotate it to put the methyl group up here. When I'm turning that steering wheel, then my OH goes back behind and then it moves down. So now back here is my OH. And then as I'm turning that steering wheel, my hydrogen, which was in back, it moves forward. So now my hydrogen is here. So now I have my ethyl group and my methyl group in the same orientation. Here my OH is in front, but here my OH is in back. So this is not the same compound. So these are not the same compound. Instead, what we have is a pair of enantiomers. If we took this molecule and slid it behind this one, we would see that the OH is reflected from the front, it's reflected to the back. So these are mirror images, but they are not superimposable, which makes them a pair of enantiomers. Now, you might find different ways to manipulate the molecule. I recommend that you try it on paper and try it with a model so that you can double check the way that you see it in your brain, make sure that you are visualizing the molecule itself in the model the same way. Looking at this next pair of compounds, again, let's try to put this one into a similar orientation as this one. So I'm going to leave this one the way it is, and I want to manipulate this one so that it's in the same orientation. Right now it's looking very different because these two groups are going back and these two groups are coming forward. So let's take this whole molecule and just rock it to the side. So just tilt it over so that our carbon is here. As we tilt it over that way, the methyl group that was in front, that is going to move back. The chlorine is still going to be in front, but now it's over on the right side. And then the hydrogen that was back, that's going to be in the plane over here. And the bromine is going to be in the plane over here. Okay, that didn't really help that much, but that's okay. Next, let's take this and just tilt it. So we're going to keep it in the same plane, but we're going to rock it up this way. So now let's just kind of move it up here. So now our hydrogen is here and our bromine is here, right? So we're just tilting it to the side. So that means the chlorine is still in front and the methyl is still in back. All right, now if we look at this one compared to this one, we have the hydrogen in the same plane, but the wrong side. So next, let's pick up this molecule and flip it over. I'm actually going to write that down here. So if we have our hydrogen on the left now and our bromine on the right. If we do that, then our methyl group flips over to the front and our chlorine is in the back. All right, so we have our hydrogen in the same place, but we need to get our chlorine up here. So once again, let's think of this as a steering wheel. So we're going to be looking at it kind of from over here, right? And so we have our steering wheel and bromine is at the top of the clock. Chlorine would be at like 4 o'clock and methyl would be at like 7 o'clock. Okay, so I'm combining my steering wheel with my clock. I want to turn my steering wheel this way so that the chlorine moves up to where the bromine currently is. So I'm rotating around this bond so the hydrogen and carbon are in the same orientation. I'm trying to turn this steering wheel so that the chlorine moves up to this position. And when I do that, what else happens? So as I'm turning it this way, the bromine that was at the top is going to move to the left, which then over here puts it into the front. Now the methyl group that's on this part of the wheel, this is going to turn this way. And so that puts the methyl group back. So now we can finally compare this representation and this representation. Our hydrogen, carbon, chlorine are in the plane in the same orientation. We have our bromine in the front and our methyl group in the back. Notice here the bromine's on the right, methyl's on the left. Here it's the opposite, but remember what this representation means. This is a tetrahedral carbon, so these 3 atoms are in the plane, and then these are going forward in front of the plane and back behind the plane. So these are really right on top of each other, and I just write them a little bit offset so we can see them. Here, they're written a little bit offset, and they just happen to be written a little bit offset the other way. This is the same thing. And so, yes, we know this is a chiral molecule just by looking at the compound itself. As we compare it to another molecule, we can see that these are actually different representations of the same compound. So please get some practice manipulating molecules on paper to where you can be able to compare them in a useful orientation.